Alright, recording has started. We're getting some feedback from everybody. I check your name. Daniela? Alright. Let me mute. I think that takes care of it. I'll unmute you later on, Daniela. Alright, 30 seconds more. Alright, if you only finished number 1, didn't have a chance to go to number 2, I'll pause a little bit after we do number 1 and let you go on with number 2. So the surface area, you find the 2 volumes. Well, you find the area of the top and the bottom, and then you find the area of the wrap. Alright, so top, so surface area, top and bottom. It's going to be pi r squared, which is pi times 4, but then you doubled it, 8 pi. Okay, and then for the volume, still for the surface area, surface area, the wrap. Now we pretend we cut it with tin snips, like this is a Coke can. We lay it out. And then the height is 5, and the distance from here to here is the same as the circumference. And the circumference of the circle is 2 pi r. When that's going to be 2, so it's going to be 4 pi. So we're going to 4 pi times 5 is 20 pi units. And when you add those two together, 28 pi square units. So if this was in meters, it would be meter squared, something like that. Now the volume. To do the volume, you find the volume of this very first layer. And the area of the bottom was 4 pi, but that 4 pi is also the volume of this first layer. Think of these as ice cubes. First layer, 4 pi cubic units. And then times 5, which is 20 pi units cubed. Alright. Give me a little feedback on this. Tell me if you got everything right. Say nailed it, Otherwise, tell me you're still working on it. If you're still working on it, give me a little details about what's the harder part for you. Okay, and also when you give feedback, from now on I'm going to ask that everybody type it in, but don't hit enter until my cue, so that we see them all at once. Okay, quick check at the feedback. Okay, so these are some ones to look at, I think. Okay, and alright. Finish number 2 if you're still working on that, and do number 3. Set up but don't solve the integrals. For the volume of the solids of revolution, A is, you're going to set up one integral to get that solution. Three A is a bit longer. I'll give you a couple more minutes. And 30 seconds more. Alright, let's look at the definite integral. So it's the limit as n goes to infinity of summation I equals 1 to n of f of x sub I star times delta x. So, and what it represents is area from A to B underneath the curve F, and your little delta x's are going to be making slices like this, and you're going to have something in here, x sub I star, could be a left endpoint, right endpoint, or midpoint. When you multiply that by the height of that point, you're going to get a area of a very thin, tall rectangle, and you sum them all up, and that's how you get in the definite integral. And then number 3. And let me pause for a moment here, and let me ask, is there anybody who's using the Canvas app on their phone? You can give us a little feedback about that. Anybody doing that?
I do.
Okay. Does it help in some way that you makes things more convenient or better?
Well, one thing you can do is use it for submitting your homework. It goes a little more quickly. I use one of the scanning apps to take a picture of my homework, and then my scanning app exports to the Canvas app, and it automatically figures out like which ones you can submit to and stuff. So you pick the class, and then you pick the assignment, and then you submit it. So that works pretty good.
And prior to doing the Canvas app, you were having to transfer it from your phone to your computer.
Yeah.
Yeah, okay, so it saves a step, okay?
Yep.
And does it give you notifications as well? Is that convenient?
No. I turned mine off because if you turn on notifications, then it notifies you for everything, which is mostly stuff I don't care about.
Okay.
So yeah, that doesn't work great, and the Canvas app doesn't work great for just looking at modules and stuff, because it doesn't go. It needs full screen to show you a lot of things. So yeah, turning in is the only thing I found it useful for.
Okay, but that could be a pretty big deal, making turning in work more convenient. Mm-hmm. Okay. All right. Thanks for that feedback. My son was using his Canvas app and finds it pretty handy. Yeah, I think he found the same thing. It was getting him too many notifications. All right, so let's go to number 3. And all right, so the curve y equals 2 minus x cuts through here. Y equals 2 minus 2x has a y-intercept of 2, slope of negative 2, goes through here. This is the area between these two curves. It's going to get revolved around this, around the x-axis. No, it's not revolved around the x-axis. And then do that. It's revolved around the y-axis. So to set up the integral, I'm going to do part 1, slice. I'm going to decide whether I'm going to take vertical slices or horizontal slices. And let me come back over here. I muted Daniela. We were getting some feedback. Taking you off mute, Daniela. Okay. And so slice. If I do vertical slices, there is no consistent upper and lower function. The upper function is the green curve, the lower function is the blue curve, only from 0 to 1 on the x-axis. From 1 to 2, the blue curve is not the lower curve, the x-axis is. So I'd have to take two integrals to be able to get this if I did vertical slices. So I want to take horizontal slices. So I'll take one representative horizontal slice. This is going to get whipped around the y-axis. What's it going to look like after it gets whipped around? It's going to be now I ran out of room on the far left, but it's not the best artist here, but it's got a little thickness to it. It's a washer, like the kind of washers with the holes in it that you put if you're screwing something on. And we have two radiuses, R1 from here to here, and then from here out to here, 2. And the area, or the volume of one of the slices, so V sub I is equal to, now if I do pi R2 squared times the thickness delta y, its thickness is, thickness is a difference along the y-axis, so it's a delta y. That gives me the area of the whole circle, too much area. I need to subtract off too much volume, the volume of the inner circle. And the R1 is from here to here, so let's call this X, no, this is not X, it's a Y. Y sub I star, let me go to black. Here is the point right here, X sub I star. X sub I star, Y sub I star. It could be the left end point of a little tiny interval, it could be the right end point, it could be the midpoint, one of those. But it doesn't even have to be one of those, but those are three of the most typical choices. Okay, so this distance from here out to here is the X sub I star. Alright, and the X sub I star, this is R1. Now, this is going to be a delta y, which is going to turn into a dy, and we need everything in terms of y's then. So we're going to take this equation, the blue equation was 2 minus 2x. We're going to take that and solve for x. So I'm going to get y minus 2 equals negative 2x. Divide by negative 2. X is equal to negative 1/2 y plus 1. Okay. And so this X sub I star and this Y sub I star are related through this formula right here. And so this is going to be negative 1/2 y sub I star plus 1. Alright, so that's going to go in for this R1 up here. For the R2 2, we have this different distance, and this one, let's call them I could use x sub I and y sub I again, but I'm going to do x sub j star, and it's the same height, y sub j star, and what's going to be true about R2 is x sub j star, which is coming from this equation right here. Now we're going to take y equals 2 minus x, we're going to solve for x, and we'll bring the x to the left, the y to the right. X is equal to 2 minus y. So x sub j star is equal to 2 minus y sub j star over there. So then we're ready to complete this. V sub I is equal to pi times, now R2 is 2 minus y sub j star squared delta y minus pi. R1 is negative 1/2 y sub I star plus 1 squared delta y. Now that's slice. The next two go very quickly. Part 2, let me go back to black. Sum V sub I. These are actually supposed to be approximately equal. It's approximately equal still. We just sum up all these. I equals 1 to n of exactly, let me put it in brackets, exactly that. All this stuff is going to go right down into here. And then take the limit, become an integral. V is equal to, and we just put a limit in front of this. Limit is n approaches infinity of all that stuff, which then becomes this integral. And the pi is in front of both, so I'm going to pull that out front. The I stars go away. 2 minus y, oops. And then the delta y, I'm factoring out, putting it at the end, minus 1/2 y plus 1 squared, and the delta y becomes dy, and then we have to determine our limits from, this is along the y-axis with horizontal slices, so it goes from 0 up to 2. 0 to 2, like this. Alright, now this is setting it up. To execute this integral, you'd have to square this out, foil that out, combine the like terms, take the integrals. It's a lot of work yet to do, but that's all that I asked you to do. Set up this integral. All right, so you don't need to give me any feedback on number 2. On number 3, tell me if you've got it totally right, nailed it. You could still write something like still a useful review or not, or whatever, nailed it. Or you can say still working on it. If you're still working on it, give me some details. Is it hardest for you to draw the picture at the beginning, to make this slice part correct, or where are you having your difficulty? Type in your feedback, but don't hit enter yet. Okay, everybody can go ahead and hit enter. Let me see the feedback. Okay, now part BB is exactly the same problem, the same region, 2 minus x, 2 minus 2x, but this time, instead of being revolved around the y-axis, which was a vertical line, it's a different vertical line, revolved around the line x equals 3. So again, same instructions. Go all the way to setting up the integral, but don't actually figure out what the integral is. Just set it up. And while you're doing this, I have a curiosity. Does anybody have OneNotes open, their own version of OneNotes open simultaneously? And how fast does it update when I put in stuff? Or does it not update at all while I'm working until later? If you've got the answer to that question, I'd be curious.
People are saying a short delay.
There's a delay, yeah?
Just a few seconds.
Just a few seconds. And then what I draw in shows up on theirs as well. Okay, cool. I'm going to copy my image from up here over. Okay, so this time we're revolving around x equals 3. And when we revolve it, we're going to get this really kind of strange shape. And we are still going to want horizontal slices. And when we wrap it around here, we're still going to wind up getting what we call a washer. So let's draw this washer. And the inner part is going to be removed. And we're going to have this time, this is my R1. Here is my R2. That's corresponding from here to here, and then from here over to here, R1 and R2. And so, for the same kind of formulas are going to apply up here. V sub I and I need to find out what R1 is and R2. Oops. Alright, so let's go to here. We'll start with this one. X sub I star, Y sub I star, some point here. And this R1, well, from here to here, this is X sub I star. But we want the whole length from 0 to 3, subtract that length. From 0 to 3 is 3, but subtract off, so this whole length, subtract off that length, will give you this length over here. And then this X sub I star is from this one right here. When we solved for X, was x equals 2 minus y. So minus y, so y star. And then, of course, that'll reduce. This will just become 3 minus 2 is 1 plus y star. And our 2, we're going to do a similar thing. We're going to use this point right here. You could call it y sub I again, y sub I star, or y sub j star. And when we, this once again, it could be also y sub j star. Okay. And this is going to be x sub j, but 3 minus x sub j star. 3 minus, now when we solve 2 minus 2x for x, we got negative 1/2 y plus 1. Y sub j star plus 1. And that 3 minus 1 is 2 plus 1/2 y sub j star. Okay, so these two go in for R2 and R1. So V sub I is approximately, now I could factor out that pi if I want. I could get my R2, which is 2 plus 1/2 y sub j star squared delta y minus 1 plus y star squared delta y. Okay, and then we sum and then take the limit, become an integral. If you wanted to, skip some of those steps and just go right to v equals right from here, that'd be okay. It'd be the integral along the y-axis, so we're still going from 0 up to 2. We'll take this pi out front, in front of the integral. And then we're going to get the ij and the stars all drop off. Here's this bracket. And that becomes your integral. Like that. Alright, so you don't need to give me feedback on this one. It's rather similar. The other one is just more practice. And let's go to number 3. Let's get the size right. Set up but do not solve. Hold on, I had a picture to go with this. Alright, find the displacement, the distance traveled, and let me just get that picture again. And I'll put it in. So, this let's go into Wolfram alpha. And what was the intervals on 0 to 5? So here is the picture, and let me put that into the problem to speed this along. Okay. So looking at this picture, it's a velocity function. This is v of t. And set up the problem that is the displacement, and also find the distance traveled. Set it up, but don't work it out. I'll give you a couple minutes. Right, 30 seconds more. Right, so the displacement is equal to the integral of the velocity function. From 0 to 5, we just put this velocity function in here. So all you got to do every time to find the displacement. The distance traveled is you have to treat every velocity as if it was a positive velocity. So as if this curve down here was really going up above the t-axis. So we would take this integral from 0 to 1 of the same thing. And then we'd have to, instead of adding this, because it'll be negative, we put an extra negative, so we subtract the integral from 1 to 5. And that's my distance traveled. So we interpret all areas as positive areas if we had a velocity function in order to get distance traveled. And give me a little feedback on number 3. Again, nailed it, or still working on it, and then tell me what you're still working on. And the problems in the homework were like this, but they didn't give you the graph. And if they didn't give you the graph, you could, create a graph by making a quick table from 0 to 5 of putting all these entries in, or, use a graphing utility or something like this. All right, so if you'll enter your feedback, put your feedback in, but don't hit enter yet. And then if everybody could hit enter now, take a look. Tristan, thought you had to take the integral first to get s of t. If I was trying to get the distance function, s of t, that's a different problem. It's not the displacement, nor is it the distance traveled. If you're trying to get the s of the t, it is the integral of the velocity function minus your original position. And then you take the integral from 0 to t minus s of 0. Okay. All right. So that's everything for the practice quiz. All right, homework. I think you all had typed in some homework problems that you wanted me to look at. Could you do me a favor and type them in again so I can see them fresh on the screen, so I don't have to scroll back? Anybody wants to look at any particular problem, go ahead and let me know. 50. This is 6.3. Question 11. 50. All right, we're not going to have a lot of time. And 50 is repeated more than once. All right. I'm going to go through number 50. I'm going to go through kind of quickly, and that's probably the only one I'm going to be able to get to here. So let's go. Where is here? This is on page 437. All right, so the directions on this is when r is revolved around about the line y equals 2. Okay, so these first equations defines region r, and then we're going to revolve it around y equals 2. And so first thing, I'm going to draw a little picture in 2 space of this region. Y equals 2. x equals 1. And then this function right here. When you raise e to a power, you always get a positive result. E is about 2.7. When you raise 2.7 to 0, you get 1. When you raise it to a positive power bigger than 1, you get something bigger than 1. When you raise it to like negative powers, you're going to get fractions, but this will always be positive. Now the bigger that x gets, the smaller it gets though, because it's negative. So when x is 0, you get e to the 0, which is 1, plus 2, which is 3. So let's go up here a little further. Okay, so this starts up here. Come on. And then it's between x equals 0 and x equals 1. Just take it when x is 1. Then you're going to get e to the negative 1/2. So, and that's going to be smaller. Let me punch that out on my calculator. Is about 0.6, about 0.61. Plus 2 is 2.61. Okay, so it goes, when you're at 1, it comes down to about here. So this is going like this. And then we have at y equals 2, x equals 0, and x equals 1. So we get this region right in here. And this is going to be revolved around y equals 2. So you're going to get kind of an image of that down here. When you revolve it around. And so we are going to take slices perpendicular to the axis of rotation. Take a slice like this. We're going to whip it around. And we'll call this x sub I star, and up to here y sub I star. And then we're going to take a slice. One slice. This gets wheeled around and it becomes a simple disc with some thickness to it. Okay. And it's just got one important dimension right up here, R1. Okay, so V sub I is equal to pi R1 squared. That's the area of the disk times delta X. Give you the volume of the disk. Now, what is R1? R1, though, is equal to, well, if you went from 0 all the way to the top here, you'd be getting this. E the negative x over 2 plus 2 that, but then you have to subtract off this height from 0 to 2, which is 2. So R1 is just e to the negative x over 2. So we're going to say v sub I, this should be approximately equal to pi times, now these are I stars. So e to the negative x sub I star divided by 2 squared, it's not dx yet, delta x. And then we sum them up, and then we take the limit to become an integral, and we're going to wind up getting pi is the integral, and from the x's it's going to go, where's my picture, from 0 on out to 1. And then, now, power to a power you multiply. What happens to those 2's is they cancel out. And so we get e to the negative x dx. And this one is going to go pretty quick. So this is going to be the integral of e to the negative x is negative e to the negative x, because if I take the derivative of that, I would get back to this. So it's gonna, I'm going to take the negative outside with the pi, e to the negative x from 0 to 1. Negative pi, when I substitute this, I get e to the negative 1 minus e to the 0. So this is negative pi times 1 over e minus 1. And if I distribute that, I'm going to get positive pi minus pi over e. And that'll be my volume. Alright, we are at a break time. So we will start again. At 6:45. If you need to talk to me for a little bit, I'll hang on for a minute, and then I'm going to mute and take a break as well. Yep, this bucket looks like about half full.
Okay.
Maybe we do that tomorrow. And if we, for some reason, if it doesn't go on or anything like that, we can go on. So what do we have tonight? Thanks for that. We have parking lot.
We have a lot of refried beans. Are you still in class, Bob?
Yeah, we're in the break.
So I'm gonna use that one. You want to use the other one? That one is better than
Oh, so Joan, they did everything except the pipe.
I thought. Why don't we go in there and,
Yeah, why don't we do it up? And then I guess we could install those lights. Like, we didn't talk to them
I didn't really do all that stuff.
about it. Okay.
Yeah, I'm watching.
Alright, Pepper, are you coming with me or do you want to see the food? There's food being cooked over there. What if they spill something? You might need to desperately get over that. Alright, you're sticking with me, Hannah. That's a good girl. Alright, let's get started again. And 6.4 is the same topic, finding volumes from a solid of revolution, but by shells instead of by disks. And when we do by shells, what happens is the slices are parallel. Do that again. Parallel to the axis of rotation. So we're going to be doing more of the same stuff today, but I'll be doing it with the shell method, and when we do the shell method, this, and not the volume so much as the surface area formula, is going to be showing up as we do this. So, number one, the region bounded by y equals 1 of x, x equals 1, x equals 4, y equals 0 is revolved about the y-axis. Let me give you about a 1 minute head start on me and draw a rough sketch, and then you'll check that as I do it in 1 minute. So just the 2D graph of the region we're going to revolve. Alright, so I have the x and the y axis here, and I'm going to go 1, 2, 3, 4, So x equals 1 is here, x equals 4 is here, y equals 0 is the x-axis. And we need to draw this one, y equals 1 over x. Y equals 1 over x. When x is 1, you get 1. When x is 2, you get 1/2. When x is 3, 1/3. When x is 4, 1/4. So now over this side it goes really huge, because when x is 1/10 it'd be 10. But we don't care about what happens to the left of x equal 1. We just do this. And then to the right of x equal 4, we don't care about it either. So we have this shape that's going to get revolved around the y-axis. So you're going to get kind of the mirror shape on the other side. 1 up to 4, where this down to here when you swing it around. And if we tried to do it the way we've been doing it so far, which is slices perpendicular to the axis of rotation, so we get disks, we run into a problem. The rightmost function is 1 over x, but only above 1/4. From 1/4 to 1, it's the rightmost function. And then the rightmost function changes and becomes 4 from 0 to 1/4. So it would require 2 integrals to do this if we were using vertical slices. If we were using horizontal slices. If I use a vertical slice, well, there's always a consistent upper and a consistent lower function. Let's take one kind of representative slice right here. So call that x coordinate of some point in here. Maybe it was the midpoint, x sub I star. And then the corresponding height right here would be y sub I star. Okay. And then we revolve this around, and it comes over across to here like this. And then we have, let's go V. So part 1, we slice. And the volume of this one slice is approximately, and alright, let's draw a picture of that slice after it's been revolved about the y-axis. It's going to look, we called this, if you'll recall from before, a shell. It's kind of like a Coke can. But this Coke can, here's a really strange one, it's super wide. And not very high. And it's got a little bit of a thickness to it. That little bit of a thickness to it right here is the delta x over there. So we are going to be finding the volume of this shell. Okay, Okay, so it's hollow, it doesn't have a top, doesn't have a bottom. It's kind of like the cylinder that we did way back over here, except super wide, not very high cylinder, and we're ignoring top and bottom. It's just that wrap that we're going to be doing here, the wrap. So we have two important coordinates for this to get this v sub I. We need from here, from the y-axis all the way out to the edge to right here. We'll call this r, the radius. And then the other thing we have is the height of this cylindrical shell here. And so the volume here, we imagine that we cut with our tin snips right here. And then we lay this out. Same height, but it's going to go really far now. It's going to go even farther than this, but let's just drop to here. And this is going to be the same height, h. This distance from here to here is the same as the circumference of this circle, 2πr. So this area of this is going to be 2πrh, and then it's got this little bit of thickness. A little bit of thickness, which we're going to call delta x. And that's how we get a volume, as we need to have that third dimension. Delta x over here. So this volume is 2πr h delta x, the volume of this slice. And then we see part 2, we sum. That's just one piece of the volume. The total volume is approximately the sum I equal 1 to n. For some, maybe n is 8 or something like this. 8 little slices. And then 2π h delta x. And then part 3, take the limit become integral. V becomes equal to exactly a limit as n approaches infinity of this sum I equals 1 to n 2πr h delta x, which becomes the integral, and we're going to be integrating along the x-axis. We can see that we're going to be going from 1 to 4. Two pi r h dx. Now I did the order a little bit different this time. I left them as r and h for quite a while, but you can see that since we're using dx, r and h have got to be rewritten in terms of x. And so we go back up to the original drawing. The x is really this distance from here to here. That's the x. And then the h is the height. Okay. So you have a representative point x sub I star, y sub I star, and the ith subinterval from here to here. That distance is x sub I star. Now, that's also the radius. So, r is equal to x sub I star. Then, the y sub I star is the height straight up here. But from that x, we know this function right here. This function was y equal 1 over x. So this, from here to here, this height is 1 over x sub I star. That's the distance over, then the distance up, you just plug it into that function. So, that's my h. X sub I star. Now this is a kind of a cool problem, because watch what happens. As I plug in r is x sub I star, and h is 1 over x sub I star. Come down here. So we can see they're going to cancel each other out. All you're going to get is v equals, let's pull the 2 pi, that's a constant, out front, integral of 1 to 4, these two reduced and eliminated, dx. Now we're going to get 2 pi, the integral of 1 dx is x, evaluated from 1 to 4. So this is equal to 2 pi. Now substitute 4 and then subtract 1. I get a 3 here, and I get 6 pi. That's the volume by the shell method. Let me highlight again the main points. That was, first thing when you slice, you have to decide, is it vertical or horizontal? I always try going perpendicular to the axis of rotation first to do discs, because they're an easier shape. But this one needed to be vertical to have a consistent upper and lower function. So then we rotate it around and we get this big old shell. This is like a really wide portion of a Coke can. And we get the volume of that, 2 pi RH. But the R and the H were cool, they canceled each other out. Alright. Questions? Everybody okay with a basic idea for a shell method? Alright, let's go to number 2. And let me ask, are you ready to try one on your own? Should I give you about 5 or 10 minutes to set this up? Just say yes if you're ready to try it on your own, or if you'd rather just watch, then say no. Just watch, or should I give you 5 to 10 minutes to try it on your own? Are you ready to go for it or not? Okay. All right. Let me.
I have a question.
Yeah. Yes, you.
It needs about the surface. It doesn't look like about volume.
Oh, this doesn't look like it's big enough?
No, it doesn't look like about volume. It's about surface, right?
Oh, okay. What it is, it's the surface area of a very wide and not very high canister, but it does have a little bit of thickness. And the little bit of thickness is delta X, and that's why it's really a volume as well. Just like on a disk, it's really the area of a circle, but then times a delta X or a delta Y gives it a little bit of volume. Does that answer your question? Yoon, is that what you were asking about? Okay. Go ahead. Let me give you. I'm going to give you about, let's say, 7 minutes or so, maybe 7.5 minutes. On number 2, set it up, get as far as you can, and then I'll do it.
There's a, here, it's ready. Serve yourself. Which is, okay. You got a taste for him? The big one, we just used it. Okay. Yeah, we're kind of, we didn't try everything we used it, but we just actually this. What happened is. This is really pretty. Isn't that gorgeous with all the different colors? What? Look, yeah. Yeah, because it doesn't,
webcam on?
I just go to here, speaker. Oh, go to.
Just search microphone.
But here it has a microphone.
Oh.
Two apps are using a microphone. It doesn't show how to.
Scroll down. There. No. Yeah.
Oh, you could. Oh well, they're seeing the screen, so I'm gonna go back to this. All right, so let me whip up a picture of this, and you can see if what you've done matches mine. So this first one, when it's x in terms of y, two ways to graph it. We're not used to this. We're used to y is something in terms of x. I can just go ahead and make a little xy table for this, but I wouldn't put in random values for x, put in random values for the y, because x is in the dependent variables position. Can't put in any negative numbers. I would put in 0, 1, and that tells me that y probably is between 0 and 4. Let me jump to 4 because I won't get a whole number output. 3. So I'm going to get 1, I'm going to get 2. Actually, I won't get a whole number output for that either. 2 plus 1 is 3. Okay. And so then, when I'm graphing this, now the other way I could have done this, besides this, and let me show you what this looks like here. Okay, x is 1, y is 0, x is 2, y is 1, x is 3, y is 4. Okay, I'm getting these points like this. The other way we could have looked at this is we could have solved this for y. So subtract 1 from both sides, square both sides, y equals x minus 1 squared. This is now a kind of a normal looking parabola, but it's been shifted 1 unit to the right. So it would be going up on the left, but we don't need that. It's this curve right here. And then that between x equals 0, which is the y-axis, y equals 0, which is the x-axis, y equals 4, which is here. So it's all of this region inside here is revolved around the y-axis. No, that's not true. It's revolved around the x-axis. We whip the shape around this way. Alright, so there's not a consistent upper and lower function, because the lower function from 1 to 3 is different than the lower function from 0 to 1. So we need to have, if we want to do it with this one integral, we need to have horizontal slices. I'm going to take one representative horizontal slice. The point that furthest out and over is my, I always label that x sub I star. Y sub I star. Over here, and it's 2 coordinates of this point labeled on their axes. And so then I whip this, so I got part 1, slice. The volume of this one little piece, when it's whipped around, it becomes, let me shrink my screen a little bit so I can fit this in. It becomes, and let me put this in green. I'm going to do it a little different this time. It's from here, I'm going to go down to here. Can't see that back part. From here, I'm going down to here. And then, so I have this, but it's got a little bit of thickness to it. The little bit of thickness is the thickness of that red. That's delta y. So this is a Coke can turned on its side. And we don't have the right end or the left end, or top and bottom if you put the Coke can vertically. Missing that is just the wrap part of this. And again, this is called the shell. And V sub I, let's do that again down here. The volume. Well, it depends on a couple things about this. One of them is going to be the, let's go to gray. Radius. And the other, we'll still call this H, as if this can was turned vertically. It's not really a height unless you turn it vertically, but we can still call it H. Okay, so if we use our tin snips and we cut it and roll it out, going to look really long. And the H is going to be right up here. And the circumference of this circle is the length, 2 pi r, right over here. And the volume of this piece is 2 pi r, this times this, 2 pi RH, and it has a little bit of a thickness to it. And the thickness is a delta Y. And that turns the area into a volume when you multiply by its thickness. Alright, so we're on the right track. We need to figure out what the R and the H are. Now, the R, well, the H, see x sub I? When you put an x sub I right underneath this, that's saying that this distance from here to here is x sub I star. But that's the same as the distance here to here, same as the distance here to here. That's R. Now, I can't leave out as x sub I star because this is a dy, but that's a good start though. Don't bother about getting it into the right letter right away. You can eventually get it there. And then the H is, for a given x, it's the same as the y for this function right here. But what's this function? This function, then, so it's the y sub I star. Oh, hold it. No. I had this wrong. The h is the x sub I star. This distance over and this distance over is all having to do with the h. The r is the height, so it's just the y sub I star. But this delta y is going to turn into dy. This y sub I star will turn into y. This x must be rewritten in terms of y. So we go back to the equation of that curve, and that is this curve right over here was x equals square root of y plus y. And we had solved it way over here when I said that's another way to graph it. And this means the same as this one. And right over here this is, so, or actually we want this one because we need to solve for x to substitute it in terms of y. Y sub I star plus 1. Okay. So that's my v sub I and this really should be approximately equal. And it's approximate because look at the right hand side of this arc. I'm kind of assuming that it's not arced straight. So even this little tiny calculation is a little bit off because that's a sideways little kind of curving arc. And when we approximate with delta y, that's just kind of the distance between those two vertical or two horizontal red lines. And then this becomes 2 pi y star square root or y star to the 1/2 plus 1 delta y. And then we're going to sum them up, and that'll get you from v sub I to v. Then we'll take the limit, become an integral, and that'll get you to v and an exact. And when you take the limit, become an integral, it becomes 2 pi. This formula, the y, just drop the I in the star, y to the 1/2 plus 1 dy. We need to look at our picture to say from where to where. And we are integrating from a height of 0 all the way to a height of 4. So 0 to 4. And alright, now when I look at this, I'm going to revolve it around. I think I'm going to get a pretty big volume. Because 4 height, go over eventually to 3 over, 3D shape. I'm going to guess something kind of big like 60 or something like this. Let's see what we get. Volume is 2 pi. Distribute this out. Let me use parentheses. Integral 0 to 4 y to the 3/2 plus y dy, and then 2 pi, and then need antiderivatives. Antiderivative of y to the 3/2 is y to the 5/2, add 1, over 5/2, which is 2/5, plus integral of y is y squared over 2, and we're integrating from 0 to 4. When I put the zeros in, everything will zero out, so I'm not going to bother writing that down. When I put the 4 in, I get 2/5 times 4 to the 5/2 minus 1/2. 4 squared is 16. Now, 4 to the 5/2. The 1/2 power means the square root. Do that first. That gets down to 2. 2 to the 5th is 32. So this is 32 times 2 is 64. 64 times 2 is 128 pi over 5 minus, now when I put these two together, 1/2 times 16 is 8, and then 2 pi times 8 is 16 pi.
Wait, why is it minus 1/2?
Oh, thank you. Plus. And then I'm going to punch this out into my calculator and see how big it is. It does look big. $130. I had kind of estimated 60, but something bigger than that doesn't surprise me. 0.69 cubic units of volume. All right. Any questions?
Yeah, I have a question. So why did you use delta Y?
Why? Say that again. Why do they use what?
Oh, why did you use delta Y instead of delta X?
Okay. If I'd have tried to use a delta X, I would have vertical slices. And notice from 1 to 3, the lower function changes. It's part of this parabola here, but it's the x-axis here. So although the upper function is one consistent function, there's two different lower functions, so I'd have to have two separate integrals to do this. Does that answer your question, Bianca?
So delta X would be vertical slices and delta Y would be horizontal?
Yes. You'd think of delta X, you're just slicing up your x-axis. And the only way to slice up the x-axis is with vertical slices. Delta Y, when you're slicing up the y-axis, the only way to do that is horizontal slices. Little pieces, this is a little piece of the y-axis, so it's called delta Y. Good clarification. Any other questions? These are kind of time-consuming problems. All right. That takes us to the end for today. And I have a little bit of time left over, so I could go back to questions that were asked on homework. So I see number 20. We did.
Excuse me.
Yes.
I have a question. Is it because we use the delta Y? Is it because next slice is always perpendicular to the delta X?
Well, I had a hard time understanding what you're. Now you said something about perpendicular.
Next slice, the slice,
Yeah.
it's always perpendicular to the X.
This slice is parallel to the x-axis, and it's parallel to the axis of rotation. We're rotating around the x-axis. When you take a slice and you rotate it parallel to the axis of rotation, you'll always get a shell. If you take a slice, if we'd have taken a vertical slice, that would have been perpendicular to the axis of rotation. We'd always get a disc or a washer. Yun, is that what you were asking about? Okay. Anything else there? All right. So we have one more question on 23 to look at. So let me go there, and Pearson signed me out. Let me Go back in. Okay. And page 436. And 23. And if you're good with this, I'll see you next time. If you want to keep watching, I'll stay here with you. I think it was 23. Yeah, 23. Okay, so we're going to take this, revolve it about the x-axis, and this, I could take horizontal slices because there's a consistent rightmost and there's a consistent leftmost, or I could take vertical slices because there's a consistent upper and a consistent lower function. I have my choice. Whenever I have my choice, I always choose the disk method. It's a little easier shape to work with. So when I revolve this around, I'm going to get what we call a washer, a disc with a hole in it, and it's got a little bit of a thickness to it. And that little bit of a thickness is a delta X. And the one slice. This is the key step. If you can do this step, you got it. V sub I is, well, it's the volume of a disk, which is the area of the circle times delta X. But we need the radius. There are two such radiuses. R1 and go all the way up, R2. So it is pi R2 squared. That will give me the radius of the outer circle, or the area of the outer circle, times delta X. That gives me the volume of the entire disk. But we have to subtract out the hole in the disk, pi R1 squared delta X. And then we have to see what R1 and R2 are. R1, well, if this one was X sub I star, Y sub I star. So R1 is the Y sub I star. So, but the Y sub I star is equal to the X, because everything has got to get in terms of X's, because we're using delta X. So this is the same as X sub I star from that equation. It's R1. R2, from here to here, Now you could use x of I star again, or you can, I've been using x of j star. Y sub j star. And it's the y, it's the height, not the distance over, but the height. But we got to do that in terms of x. Well, that's 2 times the square root of x sub j star. Let's plug it in, that x going into that function. And so we've got our v sub I is approximately pi times 2 square root of x sub I star squared. And I'll put them all as i's instead of i's and j's. Delta x minus pi r1 is x sub I star squared delta x, and then I'm going to sum them up, and that'll turn it into a v instead of a v sub I. I'll take the limit, become an integral, and it'll turn it into exactly equal. So I'm going to get v equals, and the pi will come out in front, the integral. When I square this, it becomes 4x, just the square root goes away. The I and the star, we just remove those. Minus x squared dx. We look at a picture to see where are we integrating from. 0 to what? Well, where do these two things intersect? Well, they're both equal to y, so they have to equal each other. And then I'm going to square both sides. X squared minus 4x equals 0, x minus 4 is 0, x equals 0, x equals 4. So it's over here at 4. So x equals 0 to 4. And then I'm going to have v equals, take the antiderivative. The antiderivative of x is x squared over 2, so I'm going to get 2x squared. Antiderivative of x squared is x cubed over 3. All that evaluated from 0 to 4, and there's a pi out in front. When I substitute 0 in, everything zeroes out, so I'm not going to bother with that. When I substitute 4, I get 16 times 2, which is 32. And then 4 cubed is 64 over 3. So turn this into, multiply top and bottom by 3, 96 over 3 minus 64 over 3. 96 minus 64 is 32. 32 pi over 3, and then I'll punch that into my calculator. .51 cubic units is its volume. And does that look reasonable? Yeah, going out to 4, pretty big high, looping around. Yeah, could well have that kind of volume. Any questions? All right, we will stop here. And I'll see you all on Wednesday. Let me turn off the camera.